everybody. Today I'm going to talk about the efficiency of deep learning, or actually the inefficiency of deep learning, and the trade-offs when you want to make inefficient deep learning becoming efficient. At the end, I'm going to talk a bit about what we do at Brodmann17. Okay, so as you probably all know, deep learning is the state-of-the-art in many applications, including language understanding, image recognition, and speech recognition. But that comes with a very high computational cost, especially when you deal with images, in which the underlying component is usually a very large convolutional neural networks, which consumes a lot of operations. Okay? And we're interested actually in the efficiency of the inference part, not the training. So you can think that the training is done only a single time. It could take a day or two, even a week or a month. But after this model is complete, is fully trained, you actually need to deploy it in production in many devices, some of them with very tight constraints. So you want the inference part to be very efficient. The forward passes done there, the amount of forward passes done in production is orders of magnitude larger than in training. So we're interested in the inference. So that's what I'm going to talk about today. And also I'm going to talk about edge, working on edge devices, which are actually low-power devices, not the pricey high-end GPUs, and not cloud. Working on edge actually has a lot of advantages. One of them that you're very close to the sensor. So you actually want to be very close to the sensor in order to reduce the response time. You want to be real-time. Sometimes it's critical for several applications. For example, for autonomous vehicles, you want to be able to detect an event instantly. You don't want to upload the image, then get the response. You also want to work on very cheap hardware. And also you want to maintain the privacy. For instance, if you have a camera in your house, you don't want these pictures actually being sent back, but you do want to do the processing. So let's see what tools we have to talk about the efficiency of deep learning. So this is the deep learning stack as we all know it. It's comprised out of 4 elements. We have the underlying hardware. Mainly we know the GPUs, we have CPUs, and also we have FPGAs, ASICs. We have the libraries on top, the frameworks, and the algorithms. Let's start by talking about the hardware. So what is exactly deep learning? What is done there? So basically deep learning is matrix multiplications. You take a series of matrix multiplication in the form of fully connected layers or convolutional layers separated by nonlinearity. So this is the basic computation you do in a deep neural network. So we're going to talk a lot about this multiply and accumulate operations, and how much of these are consumed by different architectures and algorithms. So this is a very important factor if you want to be efficient. The deep learning libraries, as we know, cuBLAS, cuDNN, are actually implemented these matrix-to-matrix multiplications very efficiently on NVIDIA's GPU, for instance. On Intel CPUs, we have MKL, BLAS, we have NNPAC. On ARM processors, which are very common in very low-end devices, everyday devices, because actually they've been developed for mobile phones, so they're very, very popular. We have the ARM Compute library, and recently the Qualcomm Snappy library. So all these were actually designed specifically to use all the available resources on the different hardware, mainly CPUs and GPUs, in order to compute all these very efficiently. But of course, we heard a lot recently that GPUs is very popular for training, but it's not necessarily the best hardware for inference. So the crucial bottleneck in deep learning is actually the data flow, accessing the DRAM. So ASICs and FPGAs are being developed today by large hardware manufacturers and a lot of startups. I put some figures down here. So they're actually trying to optimize the data flow through neural networks in order to increase throughput and also reduce the energy consumption. That's something crucial, critical in order to be able to run on edge devices. Okay? So let's recap. We have GPUs, very popular for training. When we want to run on low-end devices, we don't have these GPUs. We actually will find ourselves with these low-end ARM processor, and they have that much capability of running multiply accumulates. So how do you compensate for that? So we'll talk about that in a bit. Before that, let's talk about the frameworks. So on top of that, we have the frameworks. Frameworks, as we all know, allows for rapid development, research, especially for accuracy purposes, but you also can identify inference bottlenecks in these frameworks. We have a lot of flavors. We have Café, cuDNN, we all know that. The frameworks are actually built on top of these hardware and libraries. So these are actually transparent to the libraries. The user or the researchers using these are actually, he doesn't care about this. He just wants everything to be done in a reasonable time. And in the, okay, and so in the, when they had to choose between being efficient for either for training or for inference, the deep learning frameworks actually chose to be very efficient for training. Okay, so when you think about running optimized algorithms on edge devices, usually you wouldn't want to use these frameworks because they are optimized for training. Hence, they use a lot of memory because it's very beneficial in the training process to keep the weights from the forward pass, backward pass. So you have to keep all this in memory. This becomes very, very inefficient, and most of them use various kind of libraries. Okay, so efficiency, we wouldn't get efficiency from the frameworks. So the main thing I'm going to focus about throughout this talk is the algorithms. Okay, so these are the key components in making deep learning efficient on edge devices. The algorithms in deep learning are actually the deep neural networks architectures we hear about. In images are the convolutional neural networks. And making these algorithms efficient, small, fast, low amount of parameters will make them run fast on any hardware. Either it's today's very low-end ARM CPUs, either it's GPUs, or futuristic dedicated AI hardware. So once you have these efficient algorithms, you will be able to squeeze the maximums out of any hardware, either today or in the future. But today there is a barrier running on these small ARM CPUs. So let's see the evolution of convolutional neural networks architectures. So that's a bit tedious. I'll go over it very fast. So just to show you the overall flow of these neural networks design considerations and how they evolved over the year. So we have to remember that the main KPI for these networks coming mostly from academia is accuracy on academic benchmarks. They don't really care about inference. They don't care about memory consumption. They just want to make them efficient. They don't care about the size of these networks. And I'll show you how it went. So the first neural network was one of the first neural networks introduced in 1989 by LeCun, LeNet5. This was the actual first commercial application of convolutional neural networks. It was actually designed to solve a very simple task of classifying binary digits for ATM. It was comprised out of 4 layers, 2 of which were convolutionals. So they defined the basic convolutional units, convolution pooling, then a nonlinearity. The amount of weight was 60,000 weights, 440K max. That's per image. Down here, the amount of marks being consumed by the convolutional neural network, that's the most computation actually goes there. So if we want to make these networks efficient, we have to improve those bottlenecks. Going further, so we have AlexNet, 8 layers, 5 convolution, 3 fully connected. Was designed to actually solve a larger task, classifying 1 million images into 1,000 categories. So he used a lot more convolutions. Okay, again, the task was he had 2 GPUs. He just wanted to make everything bigger, use a lot more parameters in order to represent the problem. He didn't care about optimizing it, so he used various kinds of convolution, 3 by 3, 11 to 11, the same basic computation unit. He went from he reached 61 million weights and 724 million max per image. So that's starting to be much more. More weights, more computations. We see how these added up. You can see the distribution of of weights between fully connected and the convolution. Most of it goes into the convolution. 2014, going deeper. So why settle for 8? Let's go for 16, 19. 13 convolutional layers, to say the least. So actually, in VGG, something very interesting happened. So they also started to think about efficiency. So instead of using 5x5 convolutional filters, they actually stacked 3x3 convolution filters. So that's very efficient because you reduce the number of weights, you also reduce the number of computation, but then they said, hey, we have something efficient, so let's take more. So they actually reached a peak of 15.5 gigamegs per image, and they increased the amount of weights to 138 million weights. So that's just in order to improve the accuracy. So we have a very large network today in VGG. At the same year, GoogleNet, which was actually much more efficient than VGG, but still, they went from 8 to 21 layers, 57 convolutional layers. They also came up with this kind of efficient module. They dubbed it Inception. It comprised out of 3 elements. We'll see these elements repeating. So this is actually a very efficient computation unit, but stacking many of these will increase the total amount of computation in the network. You see the shortcuts over here. You see the branching. So they use many different filter sizes, and they branch the input to the output. And they use the bottlenecks. So the bottlenecks are actually being used to reduce the amount of computation. If you take a 1x1 bottleneck, you actually can reduce the number of channels before applying a much more intensive convolution. So that actually reduces the amount of computation. But of course, if you take many of that, you will reach 1.43 gigamax of operations in the convolutional neural network. So they also stated in the article they had a budget of operation. They wanted to use the entire budget, but make the network complex as possible. So that's the only thing they actually cared about. Going further, it was developed into Inception, version 1, version 3. There is also version 4 today. You can see they went to 30 layers deep, then to 42 layers deep, going from 1.86 gigamax, 2.86, and then 5 gigamax. And it always gets more weights, more convolution, more operations. So the networks are actually being designed to be more complex and less practical for everyday devices. So that's a lot of computations if you want to actually deploy this. On the way, you can see up there, they also use the same efficient design, stacking 3x3 convolutions. They also use the bottlenecks. They use the shortcuts. All these are very efficient ideas. But when you let researchers actually play with these, they will prefer to increase the depth, because in research you believe that if you make the network deep, your representation actually would be much better. The feature extraction, so-called, of the algorithm will be much more efficient. So actually, you want this depth in order to improve accuracy. But we'll see in the future that actually that's not quite true. There's a lot of redundancy in these networks, but let's continue with this. Next came residual networks, more than 1,000 layers, actually. They came up with this residual connection, actually shortcuts between different layers. So actually, in the backpropagation, you can skip layers. By that, making the training much more accurate, much more stable, and made it possible to go deeper. So they started with ResNet 34, 3.6 gigamex, 50, it went to 3.8, and then 11.3, and I didn't write the numbers for the 1,000 ways network, but that's the direction, going deeper, more computation, more weights. A lot of neural networks architectures, too short of a talk to go over all of them, but we have only this year dozens of new networks. One of them is ResNet, which actually excuse me, dense nets, which actually use the dense connections inside blocks, allowing residual connections within the same size feature maps. That's actually a very efficient idea to reuse feature computation. But once they've identified this, of course, they stacked more and more, reaching a dense net of 200 layers, which you can see the number of operation is 15 gigamex here for DenseNet. So how are we going to fit this into a low-end device? Okay, we have Resnicks. It's the same. It's a combination between Inception and ResNets. It's the same principle, actually. And over here, we see a recap of what's been going on in the last couple of years. So you hear that the accuracy increases. So higher is actually better in terms of accuracy. If you go to the right, the number of operations as you go to the right, it's much worse. Like you spend much more operations on actually applying these networks. So you see the direction is to the right and up, increasing the accuracy while using more parameters, using much more operations. So that's the way it is in the research industry, and the question is how are we going to fit it into a low-end device? How are we going to run this on everyday processors and not the high-end GPU? So throughout the years, people came out with different methods to reduce the problem. They actually found out that most of these networks are over-parameterized. So you actually can cause brain damage. It was done by Jan LeCun in 1980. Actually prune redundant weights. You can do that several criteria, either checking which weight impact the training loss or the energy, as you can see on the right hand side, or just simply removing small weights. So you actually want to make the network sparse. So you have a large network, you see that there are redundancies inside the networks in current architectures because they are so big. It doesn't make any sense that they actually use all these weights. So people thought, hey, let's throw out some of these weights. So you can see on the right image, you see, for instance, Google Net. They pruned it, they actually made it sparse, they reduced the energy in the network, and by that they also harmed the accuracy. So that comes with a grain of salt. You can prune the network, but you need to take under consideration that it might hurt accuracy. So we're starting to lose accuracy here by going smaller. And also, you need to remember that in order to exploit this sparsity in the network, you need actually a dedicated hardware to use this sparse multiplication. You can see in this figure an example of such an AI accelerator called EIE. You can see the uplift. It's hundreds times more efficient than using, he compared it himself to a regular CPU, but also compared to a GPU. So actually, you need dedicated hardware in order to run this. But you can also think of ways of pruning the networks without the need for dedicated hardware. You can actually do structured pruning, which is just basically omitting full layers out of the networks. So, and by that, you can actually use ordinary hardware. You can also do some kind of approximation, for example, Tucker decomposition in order to approximate the convolution and the fully connected. Of course, you hurt accuracy, but you decrease the model sizes. People came up even with the compact networks. For example, mobile nets. We heard a very large PR coming from Google. So mobile nets is actually a principle, a design principle in deep learning we saw in earlier version like Inception, for example. You basically take a 3D convolution and decompose it into a two-dimensional convolution followed by a one-by-one three-dimensional convolution. But that you reduce the number of weights, you reduce the number of computation. But if you take a look at these graphs, you can see that if you use less weights, you will hurt accuracy. So when you think about mobile nets, think that if you want to use this on practical everyday devices, you're going to pay for accuracy for that. And also another concept is student-teacher networks. So basically what these do, they take a very large complex network and they try to mimic it with a small shallow network. So actually the small shallow networks mimics the large networks by actually feeding its small network targets as the outputs of the large complex network. There are several works in the area. Some of them even show that it doesn't really work for convolutional neural networks. So these are some of the techniques to reduce existing networks, reduce their accuracy, but you gain some computational uplift. Another way of doing that of course, doing quantization. So we all used to train on using 32-bit floats on NVIDIA GPUs, but that's actually not good when you want it to run on hardware. So a lot of works dealing with how to quantize the weights to 16/8, even going down to 1 bit. But that comes at a price. If you see it on this table, you can see the quantization. You can do the quantization either on the weights or the activation. Of course, it's best to do for both. You see here the number of bits they use for the weights and the activation. Here you can see the accuracy drop. So if you use 8 bits, so 8 bits is actually fine, so you lose very little accuracy, and by that you actually gain a lot of boost in computation and in energy efficiency, because you can actually, most processors can run 4 8-bit instructions instead of a single 32-bit instruction. So that's very beneficial, but if you're greedy and you want to get down to 1 bit, you see the drop in accuracy there. So I guess that's something a lot of people, especially I think in the industry, trying to go down to 1 bit, below 8 bits, you will start to see the accuracy deteriorating. So the basic thing I'm trying to tell you, I guess you already understand that you need the basic design of the neural network to be very efficient, not redundant, because everything you're going to do after you have this monster is going to hurt you, either in terms of accuracy, or you're going to need special hardware. So you actually need these basic building blocks of a convolutional neural networks to be very efficient. At Brodmann17, what we're focusing on is developing real-life application for computer vision with deep learning. So we actually all of our efforts, all of our research efforts goes to how to design these networks to be very, very efficient, not only the networks, but also the algorithms applying them. I will talk about this in a bit. So, of course, when you try to work on real life and not academic or data sets or problems, you see there is a difference. Okay, just to do a rough division here. So in research, you usually use, I'm talking about images, of course, only. In images, you usually take sterile environment from the images. For instance, they're taken from Flickr, Google, usually very professional photos, whether in real life you're in the wild. Usually have large objects compared to very small objects or medium, large objects. You got all kinds of object distribution. Mainly you have the research, you have the objects in a central location, because that's the way they actually were able to collect the data. It's easier to collect data this way. And in real life, you got the objects all over. You don't have any control on the situation, usually. Research, for instance, for classification, you have a closed class distribution. For example, you need to classify 1 out of 1,000. But if you take these classifiers and you want to employ, let's say, on your private photo collection, you'll see that you have an infinite number of classes. So how is your model actually gonna handle that? So in research, you have balanced data set, highly unbalanced, and the most important, you have unlimited runtime resources, and that seriously that shouldn't even bother you, because that's not your KPI. In industry or real life, you have tight memory, you have storage constraints, and you have runtime constraints, okay? But of course, you also would like to keep the same accuracy. Okay, so a checklist, low memory footprint, high throughput, want a high recall, and very low false positive rate. That's something really crucial, because especially for applications which are consumer facing, once you make a mistake, they usually don't forget about that. It's not like you can show statistics of the data. You have to be 100% correct all the time. And okay. So we talked about the representations. I showed you the architectures of neural networks. So these are actually all these networks trained for classification, coming from academia, are great, powerful feature structures. We used to features in general machine learning problems. So CNN is the feature structure of any computer vision-based machine learning, deep learning task these days. So usually take this, you stack on top a specialized neural network, either for classification, regression, detection, and then another algorithm, and you have an application. The basic component of which is the convolutional neural network has to be very efficient. Otherwise, you won't be able to fit this on your device. So current approaches, so that's a recap of what I was talking about today. Current approaches usually take these huge, enormous networks, they prune it, they squeeze it, they do code butchering, they approximate it, whatever. Then they train, they retrain, they try to gain the accuracy a bit. So that's what usually these days approaches are doing. Whereas our technology, we've invented a new type of neural network, something very small, very efficient. So we actually can use these small, very efficient components and assemble them in a way which we get very, very accurate neural networks with very low computation need and very low memory footprint. Okay, so I'll talk specifically about a real-life task, which is object detection. Object detection is actually convolutional neural networks, the feature structure, and another regression classification layers. On top, numerous algorithms there. I won't go into details. That's in the next talk. There's a great tutorial by Girshik at the last CVPR. I advise you to go watch it if you're interested. Okay, so that's a paper coming from Google, which actually took these object detectors and compared their accuracy, and they actually did a mix and match between the algorithms and the feature extractors. So we hear about efficient algorithms for doing object detection. The most famous ones are YOLO and the star, and the diamond is SSD. You can see they are very efficient. Going left is more efficient, less GPU time. Going up is more accurate. You can see that they're very efficient, but very poor in terms of accuracy. Okay? Whereas if you go to the right hand, you can see that these circles are faster RCNN, which is not the sexiest method, but it's very accurate, actually. You can see here the labels of the different feature structures. You can see that if you use the largest or more complex networks, you get higher accuracy, but that comes with cost on running time. Okay, also SSD as an example, you can see on small object sizes, which is something very practical for real-life application, it has very poor performance. Whereas when you compare all these algorithms on large objects, you get really nice performance. So I guess on real-life applications, if you scan a big image, you want to detect something very small object with high accuracy, I guess you shouldn't use this without any modification, or maybe use a monstrous network, but then your running time, of course, will reduce. So some results we're sharing here. So this is actually our face detection. You can see that, so you can see, but I will tell you that this is actually built out of a very, very small neural networks. It's actually, for this result, it's floating point networks. We didn't do any compression on the network, any post-processing for that. And it actually runs on a GPU, just as an example. I'll later show you on ARM CPU how it works. It's 200 frames per second. That's with, I think, 30 or 40% utilization of the GPU. We didn't really care about that because the running time is enormous. And in terms of accuracy, we are comparable to state-of-the-art. And in some regions, we are even better than state-of-the-art. So this is just an example of our technology, what we're developing at Brodmann17. Very small networks, very efficient, very low redundancy, which consumes very small memory footprints, but still they achieve state-of-the-art accuracy. We don't have this trade-off because we built our technology going the other way around. We didn't start from an existing network and try to optimize that, because then you will hit a barrier, of course, because you can only go down once you take an existing network. You need to think about, we had to think about another approach. And I guess that's about it. Over here you can see Asaf. here, our chief scientist, one of the co-founder, and the model. You can see our algorithm actually running on a single core ARM A72 at 30 frames per second. So actually, this detector is able to detect 25 by 25 objects. The same technology can be applied on different objects like cars, pedestrians, and so on. It's actually the same underlying performance. And this is our great team, 100 human, as you can see. Join us, of course.